talks. It's password the same.
Okay, so similar to Mark's talk, most of the slides are from last year, but most of the slides needed some rework. So I'll talk a little bit of how to use, in general, the GlueX software. And most of our GlueX software for reconstruction and analysis is actually in its a JANA application, which we now call Haldi Recon, because we took the simulation part and put it into a different repository. So now we have this Haldi Recon, and the executable that Mark already mentioned is hdroot, and you can just execute it without any command line arguments, and you get the help that Mark showed. But usually you have some sort of key words that point to some value. And this software will only do what you tell it to do. So if you don't ask anything, you don't get anything. You are usually telling the program with a plugin to do whatever you want to do reconstruction, analysis, all sorts of other things can be done in plugins. Now, there are already a lot of different plugins available in the Haldi Recon repository. Here, these are links. There are also some plugins in the Haldi Sim repository now that are related to simulation, but you get the idea. Now, two very important plugins that are mentioned here in detail: monitoring hists. This is a plugin that just creates a lot of histograms, and you can always include this if you run the software. And then the second important plugin is DanaRest. This is actually the plugin that we use to produce REST files out of the raw data or out of simulation data. We produce these REST files with this plugin. So if you want to do that, just use the plugin and you get a REST file. And how to use it? You execute hdroot with -p plugins equals and then the plugin name. And then if you want to run two plugins, you just put the two plugins with a comma in between. So this looks fairly easy. Now, if you want to run many plugins and then maybe you have other keys and other values and you don't want to put them all into one long command line argument, you can also use config files. Here the command is not very different. It's hdroot -config and then the file name of the configuration file. But the syntax inside the configuration file is different than what I showed here. So as an example, if you again want to specify these two plugins, monitoring hist and DanaRest, you just say the keyword plugins and then a blank, an empty space, not an equal sign, but an empty space, and then monitoring hist DanaRest. Okay. That's it in a nutshell. Now, I told you there are a couple of plugins, there are many plugins actually provided, and you will probably never have to write a plugin. So I just go over this very quickly. If you want to start from completely scratch, you want a completely generic plugin that can do everything or nothing. It will do nothing at the beginning, but you can put in everything what you want. You can create it with a command like this, mk plugin. And you have to just give it a name, your plugin. These plugins can be used for anything, for monitoring, detector performance, for analysis, for whatnot. But it will really not be the focus of this presentation because we already have so many plugins, and most of the things that are useful are already done inside there. Now there's a second type of plugin, which we call reaction plugin. This is maybe already a little bit more useful to you. This is a plugin which does the analysis, which only uses the library, the analysis library in the code, and it makes an analysis. So it looks for, say, your incoming particle, your outgoing particle. It performs a kinematic fit, things like this. Applies initial event selection. And there's a different command. This is actually a Perl script that makes a plugin for you. It's called makeReactionPlugin.curl, and then you can give it a name again. You can play around with this, see what it has. It has a lot of example code already in, like, lots of example code. And the output of this reaction plugin will always be standardized, so it will give you a standard analysis root tree. I think the next talk will talk about these root trees a little bit more, and then the analysis library was written by Paul, so if you want to know more about this, you can probably also go back to the tutorial we had 3 years ago, and most of it was already there. Now, do I have to write a new plugin? Probably not. So even if you want to do an analysis, we have one plugin which is called Reaction Filter that actually does the first step of any analysis. Almost every reaction can be done with it. We still find bugs occasionally where we see that one reaction crashes or something, but in general, every reaction that you can think of can be done with this plugin. This helps us to be very consistent between the analysis because it does the pre-selection for all the reactions exactly the same way, and it also creates exactly the same output tree for all the reactions. So even if I'm looking at K plus K minus proton, somebody else can take the tree, and he doesn't need to talk to me. He can just take the tree, and he understands where all the things are. So this is very good. And another very good thing about the reaction filter is that you don't have to write any code. The setup can be done entirely on the command line, or if the command line gets too long, in a config file. You just need to know the particle types, the particle PID numbers, which are sort of the GEANT PID numbers, if you remember them from GEANT 3, but they're also more defined. So this is, again, a link to the Haldy Recon repository where you can just read the code and see which particles are defined as what. Just a very small example, I want to look at proton. Proton goes to 3 pions and a proton. So I just have to specify a reaction with a number here, reaction 1, and it says gamma, which is the 1, and the proton, which is 14, then 2 underscores for the reaction arrow, and then 7, 8, 9 are the 3 different pions, and then 14 is the proton again. So pretty simple. If you put this into a config file and run it, you will actually see a human-readable output of this reaction also on the command line. Now the number here, 1, is arbitrary, but if you have more than one reaction, 2 cannot be the same.
So if I type in 7 there, it automatically takes the pi0 and decays it also? So it looks for 2 photons?
Yes. So this is on the next slide, but there are, for all the particles, there are default decays defined in the code, and only if you want to have a decay that is non-standard, like for the pi0, it's not gamma gamma, but it's E plus E minus gamma, then you have to specify it. Okay. I think here it comes, but here's some additional input. This was our convention, and it's really just a choice to put the particles in the right order. So we order the particles in a numerical ordering, but we put the baryons at last, just to have it symmetric. So you have 8, 9, 17, which are 3 mesons, like the pi plus, pi minus eta, and then the baryon is at last. You don't really have to remember this for reasons I will come back later. One thing Jörg mentioned, default decays are defined here. Other decays, like for example pi0 goes to gamma E plus E minus, have to be specified. Like you want to have this reaction 1, the decay 1, you want to have the pi0 go to gamma E plus E minus is 1, 2, 3. So it's still very simple to read. And then also you can do missing particles. You just put a small m in front of it, which means that it's a missing proton. Or if you don't know the mass of the missing particle, you just put 0. small m and 0. All right. Now there's a bunch of other special options. You can, for example, on the command line, choose what type of kinematic fit you want. The default is 4, so the default is P4 and vertex fit, but you can also only do a vertex fit or only do an exclusivity P4 fit or no fit at all. You can specify how many beam bunches you want, default is 1, how many extra tracks, default is 3. You can not constrain the mass of a particle, like if you want to look at 2 photons but not constrain them with a kinematic fit to the pi naught, then you just put capital M and the particle 7, the kinematic fit. And then there's some unused hypothesis, some additional information that you can save to the tree. But okay, this is not so important. And you just put all the flags together with underscore in between. So F1, E3, M7. You can find out what it means. So this is one example. This is the example that I showed last year. So we have 5 different reactions. For your convenience, I also put them here in an even more readable way. So you have, for example, 2 gammas, you have a pi plus, pi minus, you have 3 pions, you have 3 pi naughts, you have a k plus and a k minus, and always a proton at the end. Now, in principle, this would already be enough to run the analysis, but since last year we had the idea, this is maybe still too complicated for you to have to remember all the particles and the names and then put them in the right order and remember all the flags that exist. So what we did since then, Thomas started this website where most of the rules that I've introduced on the last few slides are already implemented. So you can just, and this is a link, if you have the talk online, you just click here, you go to the website, you will find this menu where you can just add particles to it, remove particles, change the types of the particles, add some flags like the beam bunches, extra tracks. You can specify decays. If you check mark this little box here, you get a second level for the decay of the eta, and I want the eta to decay into 3 pions, and everything will be written for you and will appear in this box here. So even if you don't want to even submit it to some launch or something, you just want to see how the config file code would look like, you can just go to the website and type it in, and it will appear here. And then you can just copy it out and put it in a config file if you want. Now, what we also use it for is for analysis launches where not everybody runs over these terabytes of REST files by themselves, but we run everything for you. You just have to use the website, put in your reaction, submit it here. It will be saved to some sort of database, and then it will be run together with many other channels. And this efficiently uses our computing resources and also the tape access, because most of the REST files cannot stay on disk on the cache, what Mark mentioned all the time, but they have to be retrieved from tape. And this, if you do this for 100 channels individually, this would put a lot of effort to the tape library. So it's better to get it once and then run all the 100 channels over it. And again, this is also the big advantage. The output that comes from the reaction filter and also from these launches, they're in a common format. So anybody can look at it. So not everybody has to run exactly the same reaction for his purpose or for their purpose, but we just run it once, and then people with different purposes, like the pi plus, pi minus, pi zero channel, can be looked for. You can look for etas, you can look for omegas, you can look for other things in the same tree. So it's good that the results are in a common format. And we regularly rerun these things, even though now we have to start looking how we handle the different periods. So for now we only have one website to run over the main over the over the data that we always looked at, 2017. But now since 18 is coming online and the new things, we probably have to work on this a little bit more. Okay, just a few words on default cuts, but this is mainly for reference, and you can just click on the links and look here. So a few of the standard cuts are really applied for all the reactions. Doesn't matter what you do. You did not specify any cuts here because they're already defined for you. These are cuts on the minimal shower energy, which has to be 100 MeV. There's some PID, there's exclusivity, invariant mass cuts for if you specify a special decay, and these things. So all these cuts, they are already applied at runtime, so that the trees that come out are not too big. But if you're more interested, you can just print all the default cuts with the command line option here that you can also put in the config file. Now there are a couple of cuts that we saw that maybe are for a particular reaction are are too tight. For example, the shower energy for the sigma K analysis was actually too tight, and we had to run a separate launch over the data because with custom cuts, which can be done also on the command line, but they will be applied to all the different channels. So you can try it out at home, play with the cut. If you want to open something much more and you think you will get more events, please do. And then once you found the optimum cut, you can just report it and see. Maybe it's useful for everybody. But first, you can just use the command line options to play around with the cut and find out if it's really worth it. For example, here I just as an example set the low invariant mass cut for the pi0 to 0.1 GeV. I don't even know what the default is, but you can play around with everything: missing mass square, missing energy, timing, particle identification.
You say this option. This option is exactly the same file as for the parameters. Is the same file.
Yes. You put everything into the same config file, and it has the same syntax. So it's the key file, the key, and then the value, and a blank in between. Okay. So only very rarely you will need to write your own plugin. Only if you really have to do something very special, like apply cuts that are not predefined in the analysis library, or you want to play around, do custom studies, then you have to write your own plugin. But most of the things can be done with the reaction filter. Okay. And then a second thing that I wanted to mention, if you run the reaction filter, you get a histogram file, and the histogram file will actually have automatically generated some useful histograms. For example, it will show all the cuts that were applied in the analysis. Even though you didn't specify any of the cuts, all the default cuts will be plotted here, and also their effect on it. So this is the number of input events, and then this is also for pi plus pi minus pi0 proton. So it asks, has it even the right number of particles? So you see most of the events do not even have the right number of particles. And then you see a couple of fits, a couple of cuts, like the convergence of the kinematic fit, which drop down these events again. And here all the PID cuts that are so loose that they actually don't do much. Okay, so every histogram and every cut action is registered in this histogram. And if you want to know more about what happens actually in this big drop from the input to the has-particle combos, there's also another histogram, but this is starting to become more involved. You have to know more about what it exactly means. Okay, first things is easy. You have the number of input events, and then do you have the minimum number of particles? Do you have the maximum number of particles? And then a couple of other things. Missing mass cut. And the last bin here is actually the first bin here. Okay. And this is just another representation where the combos are created and then destroyed again. It's a bit more complicated. But yeah, I think that's everything I wanted to tell you. If you have questions, come to Slack or to the GlueX help list or something like this.
Yeah, or ask now.
Or ask now, yes.
So questions for Alex?
Yes.
Is there a location where we could get the information about what each of those cut actions actually are, like in skim events, like what that is? Or is that just ask on the
There is a lot of this in Paul's presentation here, which is a link.
Mhm.
If you can't find it there, then you will probably have to either look into the code or ask somebody else to look into the code.
And the second question, why is it in Paul's presentation, does it have a -p combo, and in yours it's just combo with no dash in front of it for the commands on the cuts? Like what?
Is for command lines, like for the HT group,
Okay.
-p and then
Right.
thing, but inside a config file, lines.
Right. We had this confusion already. So if you have it in a command line, it always starts with -p, and then you have a key and the equal, and then some value. While if you put it in a config file, there's no -p and no equal. It just looks like this. Parameter, right? Okay. Makes sense.
Other questions?
Yes.
Last slide you were saying about dangling vertex in int mask cuts. That means, like, are you taking the primary vertex and secondary vertex into consideration?
Yes, the analysis library does this for you. So if you have a reaction that has a lambda that has a secondary vertex, it will, if you tell it that it has a lambda, for example, through the website, and you say there's a lambda, then it will know.
How do we know that the secondary vertex is forming at this point of from the target?
So by default, there's no cut on the flight distance. So it could be almost exactly the same as the primary vertex, but it can also be a longer distance. But there are ways to cut later in your analysis after the tree is done to cut on this distance.
So if I have a secondary vertex in my analysis, so I have to write my own code.
No. So the tree is just a pre-selection. You will have all the events, also with the secondary vertex that is properly fitted, but there is no cut on the distance. So it will be it will be somewhere in the tree, but if you want to apply a cut, then you have to do it afterwards.
Okay, any other questions?
Choose the word should do it.
Yes.
Because we should not copyright from the start. Never do that.
Okay.
I just have one more comment. The custom cut stuff is not available through the web. Nor are there any plans to have it. Yeah, so if you want tighter, if you want looser cuts, then the default, you need to do your own running of reaction filter with your own config file.
No, I mean, that means that you need to coordinate with who's ever running
Or
that. Because we don't want people to be running over the full data set.
It's true, but I don't want people looking at the web page wondering how they can loosen or tighten cuts,
that's
because
true.
that is
That is true. So one thing that is maybe
Better have a really good reason to change that.
right.
That's the bottom line.
That's what I said. Like you can use on a small sample, you can use the command line cuts and just try it out and convince us that it's useful, and then we can think about running over the whole data set with your cuts. but you have to convince us first.
There was an example of that.
There was an example, which is the K-sigma analysis, where it really made sense.
I'm not sure it makes sense that number is the same for beat Calvin and Cal.
That doesn't have to be. There are two different.
Kinematics. GlueX was designed, the threshold was supposed to be like 60 MeV.
Well, so these are tuned not just for physics, but for practicality. If you ask for a reaction that has 8 photons in it, so there's practical cases. But if someone comes with an analysis to say 15 EV photons are relevant, then you should go forward with an analysis launch that uses that.
And don't worry if it was too much information. Just come back and read it slowly and just try it out in the command. There are examples also in this group directory that I linked somewhere. Yeah, so they're here. There's examples, and you can just run it and try out different cuts and things like this.
All right.
Yeah, sorry.
One more?
Yeah, and maybe one other thing to point out is that, especially if you're just trying to look into something, so there are web pages, which I don't know if you'll enter to, for reactions that have already been to run over the data. So, especially right now, if you're trying to look at something simple, there's a very good chance that your reaction has already been. So take a look at that before you submit.
Good point. Yep. Okay, then thanks, Alex, again.